Quick revision video on electron configuration. So we'll start with the essentials. Electron shells or energy levels are made from subshells. Subshells are made from orbitals. An orbital is a region of space around the nucleus which can hold up to 2 electrons with opposite spins. At A level we look at orbitals s, p, d and f, and at A level we look at shells 1 through to 4, in other words hydrogen, all the way to Krypton. So we're going to break each type of orbital down now. So we'll look at s orbitals first. So s orbitals can hold 2 electrons. They've got a spherical shape. Each shell or energy level contains one s subshell. S subshells are made from just one s orbital, and so an s subshell can hold 2 electrons. So if you had to draw an s orbital or an s subshell, you would draw something like that. So you need the x, y, z axes to give it its 3D perspective. P orbitals now, so they can hold 2 electrons. They've got a dumbbell shape. Shells 2 to 4 contain one p subshell, so we don't have one in the first shell. P subshells are made from 3 p orbitals, so therefore p subshells can hold 6 electrons. Each orbital can hold 2, remember. So that's what the 3 separate p orbitals would look like. So this blue one here has been drawn along the x-axis, so that would be classed as the px orbital. There's your py orbital, and there's your pz orbital. If you put them all together in one diagram, you get something like that. That would be the p subshell. So this can hold the 6 electrons. D orbitals now. So D orbitals can hold 2 electrons. Shells 3 and 4 contain a d subshell. D subshells are made from 5 d orbitals, so therefore the d subshell can hold 10 electrons. For OCRA, that's what I teach, the shapes of the d orbitals aren't required. That's what they look like, and if you put them all together for the subshell, they'd look something like that. And f orbitals finally can hold 2 electrons. Shell 4 contains an f subshell. They're made from 7 separate f orbitals, and so the subshell can hold 14 electrons. And again, not required at OCR, but that's what they look like. And obviously all 7 of them put into one diagram would be the subshell. So we'll look at how to fill up the subshells now, and again we're just going up to z equals 36, so we're going up to Krypton. So when electrons are added to atoms, they occupy the lowest energy subshell first. Once that's filled, they go into the next lowest energy, and so on. And when you're in a subshell, the orbitals all have the same energy. So the rule is, or Hund's rule, is the electrons occupy orbitals singly before pairing up. So there's your energy ladder for the subshells. So we'll just label them up now. So we've got 1s, the lowest, 2s2p, 3s3p. Bit unusual, 4s comes next, then it goes back to 3d, and then it goes to 4p. So for example, if you were putting 7 electrons into a nitrogen atom, obviously you'd start with the 1s subshell. That's full. Go to 2s, that's full. And we'll just bring in Hund's rule now. Half fill, and then that's it. So we'll look at how to write electronic configurations now. So we can write them fully, or in terms of subshells it's sometimes called, shorthand, and the electrons in boxes version. So we'll use cobalt as our example with its 27 electrons. So there's the full, or in terms of subshells. And for shorthand you go to the noble gas before the atom, so argon in this case, and then you start filling up from after argon. So argon configuration, 4s2, 3d7. You can write these in any order, so you could put 3d before 4s. Likewise for this one. and electrons in boxes would look like that. Just be careful for the Hund's rule in the 3D subshell there. So very quickly we'll look at the configurations for the first 36 atoms, hydrogen through to krypton. So hydrogen's 1s1, helium's 1s2. So second shell now, so it's 1s2, 2s1, 2s2, and then we're going into P now, so 2p1, 2p2, 3, 4, 5, 6. So third shell now, obviously all of this that's already been filled, 3s1, 3s2 for magnesium, and then we jump to the 3p subshell, so you get those, and then fourth shell, so potassium and calcium, obviously all of this is full now, so we'll pick it up at 4s1, 4s2, and then when you get to the transition elements, if you remember what fills after 4s subshell, it's the 3d, so scandium is 3d1, 3d2 for titanium, vanadium's 3d3, chromium breaks the rule a little bit, it's not 3d4, it's 3d5. So its configuration is 4s1, so argon, 4s1, 3d5. And then pattern picks back up again, so we've got 4s2, 3d5, 3d6, 3d7, 3d8. And then copper's not what you think, it's not 4s2, 3d9, it's 4s1, 3d10. And then zinc's just 4s2, 3d10. And then we go to the 4p subshell, and they just fill up as you would expect, 1 through to 6. Configuration of ions now, so ions have either lost or gained electrons, so the magnesium atom in the first one has lost 2 electrons, sulfur's gained 2, iron's lost 3. So we'll just look at those now. So 1s2, 2s2, 2p6 for magnesium, 2 plus, that for s2 minus. I'm going to explain the next one because there's an extra little bit to this. So that's the configuration of the Fe 3 plus ion. So the rule with transition metal ions is, remember 4s fills before 3d, but we also lose the electrons for the transition metal ions before 3d. So the atom configuration is all of this, so that's the argon configuration there, 4s2, 3d6. So we need to lose 3 electrons, so we're going to get rid of those 2 first, and we've got to get rid of 1 more from there, and so that's where that comes from. Just finish with this, blocks on the periodic table. So there's a sort of colour coding of the periodic table into its 4 blocks. So the lilac is the S block, the green is the P block, the blue is the D block, and the orange or red is the F block. So what does the block show us? It shows us which subshell the highest energy electron's in. So all the S block elements, their highest energy electron is in an S subshell, P, D, and F. And you'll notice helium's a bit of a rogue one there. In some periodic tables you actually see it here, but in a lot of them it's placed in here, so it looks like it belongs to the P block. It's actually an S block element because its configuration is 1s2, so its highest energy electrons in an S subshell. Why do they do that? Because it's so similar in properties to the other members of group 0, then it's put there instead.